for this great conference. I'm going to be talking today about a sort of introduction to generalized geometry, and possibly towards the end, I'm going to talk about G-structures. And we've already seen some of the applications of this kind of language, particularly in Chris's talk yesterday. So I'm going to talk a little bit more maybe about the mathematical aspects and try and give some intuition as to why the geometries take the form that they do. So I've written down some sources that I found useful when I was learning this subject. They're by no means sort of exhaustive, but that I found them particularly useful. So if you want to come back to these at some point and look at them, I've written them down here. And I've also written some differences from what I'm going to be talking about versus what you probably heard yesterday or in some of the other sort of generalized geometry talks. So first of all, everything that I talk about is going to be globally smooth and single valued up to obvious gauge transformations. So that means I'm going to have no monogamy around cycles, and everything's going to be sort of a globally geometric space. So this is going to differ slightly from what David Austin was talking about yesterday. And I'm also going to take all of my derivatives to be just along the physical dimensions. I'm not going to extend the space-time by adding coordinates in any way. And so I'm not really going to be talking about dualities here. Everything I talk about will be genuine symmetries of the theory. And so I won't need to talk about a section condition. It'll be sort of automatically implied. And so it's slightly different from double field theory or exceptional field theory in that sense. And finally, everything that I do will be restricted to what I'll call the internal manifold. And I'll make that more clear in a minute. So I'm not really going to talk about the tensor hierarchy at all. I'm also not going to discuss some things that I could have discussed today, but I'm not going to. An idea of twists or gerbs. These are often written in generalized geometry papers, and they are very important if you want to understand how flux plays a role in these theories properly. But just due to technicalities and time constraints, I'm not going to talk about it. But if you want to learn about it, come find me in the Gather Town or something like that later. And I'm also not going to talk about G-structures in terms of this thing called a frame bundle, which again is really, if you want the proper rigorous way of talking about G-structures, we should go via the frame bundle, but I'll go through a slightly more simple and kind of more well-known way of talking about G-structures. So hopefully by the end of the talk, you'll have a better understanding of what generalized geometry is. You can see that it's sort of a natural framework in which to describe string backgrounds. And on a more mathematical end, it's really just an extension of differential geometry to include larger gauge groups and larger structure groups. Now, the layout of the talk is going to be in two basic chunks. The first chunk, which is going to be most of the talk, about 3/4 of it, will be just constructing generalized geometry. So we'll go through the ODD construction and the EDD construction. And the last quarter, I'll sort of talk quickly about G-structures, and I'm just going to be firing facts at you quick and fast, basically. But I think it's important you see some examples of G-structures because they are often discussed in papers to do with generalized geometry. Now, just before I get going on the first section, I just wanted to do a couple of apologies. First of all, I live on a main road pretty close to a police station. So if we hear sirens, we're just going to have to push through. And also this stylus pen has a little button on it, which brings up a menu on the screen. And that button is right next to my thumb. So guaranteed at some point in the talk, I'm going to press that button and the menu is going to come up. So again, just ignore it and we'll come back to the screen when that happens. So let's begin with the first section, constructing generalized geometry. I'm going to start with type 0, which for me is really GR. And let's have a think about what kind of fields we have in this theory. Well, we just have a metric, right, in GR. And what's the gauge structure? The gauge, there we go already. The gauge structure is just diffeomorphism invariance, right? This is a theory of gravity, so we need diffeomorphism invariance. And if I put the theory on a torus, then there is a global GLD symmetry. Now we know GR is a geometric theory, we can formulate it in terms of differential geometry. And that means that it's built out of tensors that exist in bundles that satisfy the following. First of all, they're sort of diffeomorphism invariant bundles. And secondly, they have a natural GLD action on those bundles. Basically meaning that all the tensor fibers exist in representations of the GLD group. And this for us will be the equivalent of a GLD structure. This is what we mean by GLD structure. So what kind of bundles do we have? Well, a very natural one we have is the tangent bundle. Sorry about this. Which is often written by T, that's how I'll denote it. And the fibers here transform in the fundamental of GLD, which I'll often just denote as V, fundamental vector space. And we also have a slightly different one, which you may not have come across before, but is important in terms of G structures, is what's called the adjoint bundle, which is often written ad F. And this equals T tensor T star. So it's the tensor product of the tangent bundle and the cotangent bundle. And here the fibers transform in the adjoint representation of GLD. Now there's a question, I should say that there is sort of a natural action of this adjoint bundle of ad F on any GLD bundle. Basically because it exists in the adjoint representation. This just acts basically by matrix multiplication on any adjoint bundle, on any GLD bundle. So in particular, the tangent bundle, but also any other tensor bundle you want to define. Now we want to ask, how do diffeomorphisms play with this GLD symmetry? Often they're conflated, but for me they are slightly different. But we know that if phi from M to M is a diffeomorphism on the manifold, then d phi, the differential of this map, takes tangent spaces to tangent spaces in an invertible way. So d phi acting on a particular tangent space is an element of this GLD group. And so in this respect, diffeomorphisms and the GLD play nicely together. They sort of form part of or act in a very similar way. And we can make this slightly more precise by saying infinitesimally a diffeomorphism, or a sort of linear diffeomorphism, looks something like a transport term, which takes us from the point P to the point phi P, plus an adjoint GLD piece. And again, we can make this even more rigorous through the Lie derivative. So we know that sections or vector fields, sections of the tangent bundle, parameterize local diffeomorphisms, i.e., there exists a map, which I'll call L, from sections of the tangent bundle, or vector fields, to the Lie algebra of diffeomorphisms. And it just takes us from V to the Lie derivative along V. And we can always write, we know how to write this in terms of sort of coordinates roughly. We can write LV is the contraction of V and the differential minus dV. So this looks like a transport term. And this guy looks like a GLD piece. And indeed, if I were to put indices on this, which I'm going to avoid doing for the most part, but if I were to put indices on this, it would look like a T tensor T star piece. Now we know that the Lie derivative satisfies a certain set of properties. So what properties does it have? Well, the first one is that it acts as a differential on itself. This is going to be written slightly differently to the way you normally see it. But I can sort of, this is what I mean by acts as a differential on itself. And two, it acts as a differential on functions. So I take the derivative of V on F multiplied by X plus F LV X. And we should note that one really is saying that the Lie derivative, is covariant under diffeomorphisms. It's sort of the most generic, or one of the most generic differentials you can have that are covariant under the full diffeomorphism group. We also know that it satisfies some other properties. So we know that it's anti-symmetric. And you can write it in terms of a bracket. This is an equivalent way, but this bracket satisfies, the Jacobi identity. Okay, so that was sort of a quick whiz recap of conventional geometry, things which I'm sure lots of you already knew. But we can use this intuition to build ODD geometry. So now we're going to be looking at type 1 theories, or the Never-Schwarz sector of type 2. So let's look again. What is the field content of this theory? Well, we have a metric, and we now have a B field, which is an anti-symmetric field, a 2 form. And we also have a dilaton, which I've written in red, sorry. I'm probably going to ignore it for most of the applications, but I'm going to put it here because in a lot of papers it is included, and it changes the analysis ever so slightly. We also have a gauge structure, which, of course, this is a theory of gravity, so we have diffeomorphisms. But we also have gauge transformations of the B field, which is just a shift by an exact 2 form, like this. And again, we have a global symmetry on TD, if I put it on a torus, where now it's going to be enhanced from GLD to an ODD symmetry. And if I'm very careful about including the dilaton, what I really need to do is include an R+ factor here. And we should just note that GLD is a subgroup of this. So now what we want to do is we want to do something very similar to what happened with the differential geometry case, but now with these enlarged gauge groups and enlarged structure groups. So I'm just going to write a definition. The generalized diffeomorphisms are the combination of the form field gauge transformations and the diffeomorphisms that we saw before, often written like this. GDiff is equal to the semi-direct product of diffeomorphisms and closed 2 forms. And sort of if I look more globally, I'm allowed to change by any closed 2 form, not just an exact 2 form. And sometimes you'll see it written by this extension. If you know what this means, great. If not, don't worry about it. I'm just going to write it down. Sometimes you'll see this written this way. If you don't know what that means, don't worry. So now we want to build a geometry that doesn't have a GLD structure, it has an ODD structure. So we want to enlarge the structure group from GLD to ODD. And basically what this means is we want tensors that now transform in ODD reps, not GLD reps. But how do we figure out which tensor bundles are the ones which transform in ODD reps? Well, this is the method, and this is what you do all the time. So the method is you first pick your favorite ODD representation. You then decompose under the GLD subgroup, this sort of one that's picked out precisely by the underlying manifold. And this will decompose your representation in terms of fundamental and the dual of the fundamental GLD. And then you just assign the fundamental representation to the tangent bundle. And you build up your bundles in this way. So let's do some examples. So what is the fundamental representation? R1. If we decompose this under GLD, we find that it's V plus V star, the fundamental of GLD plus the dual. And so this gives us the natural definition of the generalized tangent bundle E takes the form T plus T star locally. So we want a bundle where the fibers transform in the fundamental representation. We decomposed under GLD and we found that it had to be of the form T plus T star. And this is only a local prescription. Again, I'm not going to talk about twists or gerbs or anything like this, where we talk about more global aspects of what it looks like, but this is basically the picture. So note, there exists an ODD invariant in a product on E given by the thing that we know it usually takes. Okay, where this hook notation that I've written here just means contraction on the first index. So normally what we see when we talk about generalized geometry, or when you go to these papers, is they'll say, oh, we want to have an ODD structure. Look, T plus T star has an ODD structure, we're done. What I wanted to do here was try and come at it from a slightly different angle and say that you necessarily have to take T plus T star if you want that fiber to be in the fundamental representation. This is basically the only thing you can write down if you want an ODD structure. We can make this more rigorous again if we go back to frame bundles, but I'm not going to do that. So we have the generalized tangent bundle. Another important bundle or representation is the adjoint representation. So now we decompose this under GLD again, and we find it's wedge 2V plus V tensor V star plus wedge 2V star. So this gives us the natural definition of the adjoint bundle, which is often written ad F tilde, is wedge 2T plus T tensor T star plus wedge 2T star. And if I want to include that R plus factor, which I talked about before, for which for the most part I won't, we need to include an extra factor of R here. Okay, good. Again, there exists a sort of natural action of this bundle on all ODD bundles. Including the generalized tangent bundle, but all other bundles as well. And I'm not going to write down what that action is. You can find it in some of the references which I gave before. But roughly speaking, you can see that the bivectors, these pieces here, are going to move you up in the space, and the two forms are going to move you down in the space, roughly speaking. You see how that works. And okay, I should also point out, there is this sort of very special subset here, which looks roughly like GLD plus two forms. So there is a very, very special place in there within the ODD group or the adjoint representation, which looks like something to do with our GDIFs. So let me just give one more bundle, which is often cited in generalized geometry papers on ODD, and that's the generalized spinor bundle. So we have a spinor representation. Wow, really pressing that button a lot today. We have a spinor representation of ODD. Remember, we can define a spinor representation of any orthogonal group if we, lifted the double cover, but that's fine, we can do that. And if we decompose it under the GLD, we find that it looks like even or odd polyforms, where this is a chiral spinor representation. You can define a chirality operator. So you have positive and negative chiral spinors, and those correspond to either even forms or odd forms, where what I mean by this is wedge even is 0 plus 2 plus 4 forms plus, dot, dot, dot. It's the formal sum of these different differential forms. So again, this gives us the definition of a spinor bundle, or generalized spinor bundle, which I'll denote with the same symbol, which is just even and odd polyforms. Just a little warning. This is actually an ODD cross R plus bundle. So here we really need that R plus factor to define these properly. Often this is ignored in papers, but really you do need the R plus factor here to define this properly. Okay, so let's go back to this question of how the generalized diffeomorphisms play with this ODD structure. We want all these bundles to be generalized diffeomorphism invariant, otherwise we're not really building a consistent theory to build our string theory out of. So let's try and understand, are these G-diff invariant? And remarkably, they are, yes. And this is precisely because if I take any generalized diffeomorphism acting on a tensor bundle, we can always decompose F as the combination of a closed two form and a diffeomorphism. Now recall that d phi at a point looks like a GLD action, and B now is a closed two form. And precisely because of this identification here, we notice this sort of very special subbundle. These transformations exist within the adjoint bundle. They exist within the ODD action. So roughly speaking, these guys at a point look like an ODD transformation. And we can kind of define this a little bit more rigorously, like we did with the diffeomorphisms. So infinitesimally, a G-diff looks something like a transport term plus an adjoint piece, ODD. And we can make this more rigorous with the Dorfman derivative, or what's sometimes called the generalized Lie derivative. Okay. So much like vector fields parameterize our diffeomorphism transformations or diffeomorphism symmetries, now generalized vectors, sections of the generalized tangent bundle, parameterize infinitesimal G-diffs. Or more carefully, there exists a map, which now I write with calligraphic L, which takes sections of E to the Lie algebra of the generalized diffeomorphism group, where V, which is a combination of a vector field and the one form, gets mapped to LV, which can be written like this. So we see here, this is the diffeomorphism piece. This is just the genuine Lie derivative. And this guy looks like closed two forms. Now we can write this in a sort of ODD covariant way. We can write this like this, where this dot is the natural contraction of E and E star, the dual space. And the cross add is a projector from E star cross E to the adjoint bundle. So you'll see this bit looks a little bit like a transport term. And this bit now is an ODD piece. And if I were to write this in indices, like copying what Chris did yesterday, you'll see that you can write this like this. Where this is now the sort of projector. I should point out again, I'm not extending this differential to act in 2D dimensions. This really is just a d-dimensional differential at all times in this analysis. So we've kind of found this Dorfman derivative, which generates our gauge transformations. And it looks something like a transport term plus an adjoint ODD. And it has certain properties. So let's go through the properties. First of all, it acts as a differential on itself. So this is already a little different to double field theory or exceptional field theory. It also acts as a differential on functions. But now we have to be a little bit careful because the vector field is a combination of vectors and one forms. So we have to first map onto the vector fields, which I'll write like this, and then take the differential, where this A is called the anchor. Now, roughly speaking, for us, this can just be a projection onto the tangent space bit. But if I was a bit more careful about global aspects and worried about twists and gerbs, this anchor map is a little bit more complicated. And in fact, it's fundamental to the definition of the generalized tangent space. This is where we differ probably most fundamentally from double field theory, in that there you're extending the space-time. So you have no real well-defined notion of what the tangent bundle is, no predefined notion of what the tangent bundle is, let's say. So you can't define this anchor map. Whereas here for us, it is sort of fundamental to the definition. Okay, well, let's just go through some other things. This collection, E with the anchor map and the derivative, define a Leibniz algebroid. And the first condition implies that L is covariant under the full group GDiff. Or if you want to write this in a slightly more fancy way, you might say that generalized diffeomorphisms are the automorphism group of the algebroid, E, A, L. We also have some further conditions, which Chris talked a little bit about yesterday. So now we have that it's not antisymmetric, but it's sort of antisymmetric up to an exact piece. And we can define an antisymmetric part, which is often written with this doubled bracket. It's called the Courant bracket or generalized Lie bracket. And now this is an antisymmetric bracket, but it doesn't satisfy the Jacobi identity. It again satisfies it up to a sort of trivial piece or an exact piece. And this is sometimes called Lie algebroid up to homotopy. So I think Alex in the next talk will talk a little bit more about these kind of ideas. And finally, I should say that the collection E, A, the inner product eta, and this antisymmetric bracket define a Courant algebroid. And it's exact, which means that the following sequence is exact. Again, if you don't know what this means, don't worry about it, but just for those who do know, there are non-exact Courant algebroids that are important in generalized geometry. They're important in heterotic backgrounds, but I'm not going to talk about those. Okay, so now we've developed this theory. We've developed the ODD theory. We know that it's got to be defined on bundles that are ODD representations. And we've defined this derivative, which gives us all our gauge transformations. And this is for ODD. So now we're going to do a quick run through what happens to M theory. And largely the story is the same. It's just you've got different groups and you've got different gauge symmetries. But really the message is going to be very similar. How am I doing for time? Okay. So I'm going to make some assumptions. Firstly, I'm going to assume that my 11-dimensional manifold is a cross-product manifold, where this external piece is either Minkowski or ADS. And this guy is a D, is 11 minus D, less than or equal to 7-dimensional internal manifold. So well, I'm also going to assume the full 11-dimensional metric takes a warped product form, and that it only depends on internal coordinates, and that I only have internal indices on my fields, which roughly means that I can restrict to just the internal manifold. And from now on, I'm not going to say any more about this. I'm just going to assume that we're working on this internal manifold. So what's the field structure? Well, the fields that we have this metric, which is really just the internal metric. We have this warp factor that I talked about. We also have the 3 form. And as Chris talked about yesterday, we also need to include the dual of the 3 form, the sort of magnetic part, to ensure that we have a full exceptional symmetry group. So this is now a 6 form on the internal manifold. What's the gauge structure? Well, again, it's a gravity theory, so I have diffeomorphisms. I also have normal form transformations, but the one for the C tilde, the 6 form, is slightly more complicated, and up to factors of a -1, which I always get wrong. It looks something like this. And I have a global symmetry if I put the theory on a torus, and this is now an EDD cross R plus symmetry. And now this R plus factor is really important. We can't get rid of it. Unlike in the ODD case where you can kind of ignore it, this time it is really fundamental to the analysis. So what are the generalized diffeomorphisms in this case? The G-diffs are the semi-direct product of diffeomorphisms, closed 3 forms, and closed 6 forms. So we see it's a very similar structure, but just slightly different form fields and closed gauge structures. And we want an EDD cross R plus structure. So what do? We do exactly the same thing we did for ODD. You pick your favorite exceptional representation, you decompose it under GLD, where this has a well-defined subgroup, GLD subgroup, and then you just assign the fundamental to the tangent bundle. That's it. So examples. The fundamental R1. This decomposes as V plus wedge 2 V star plus wedge 5 V star plus, and then there's a weird bit, but we do need to include it if you want a full representation, is this. It's a V star tensor wedge 7 V star. And we see this equals 0 for D less than 7. So it's only included in the E77 picture, but it is important. So this gives us our tangent bundle. We just assign V to T. That gives us our generalized tangent bundle. The generalized tangent bundle is E equals T plus wedge 2 T star plus the rest of the stuff. And again, this is a local prescription. If you want to talk globally, we'll have to talk about twists, and I'm not going to go into that. And the other important one that we often see is the adjoint representation. So this is EDD plus R. And this decomposes under GLD as wedge 6V plus wedge 3V plus V tensor V star plus lost my train of thought, wedge 3V star plus wedge 6V star plus R. And again, this automatically gives us our adjoint bundle. The adjoint bundle is often, again, written ad f tilde, and it's precisely what we've written down here, wedge 6t plus wedge 3t plus ... So some remarks. There exists EDD invariant tensors on E, which define the EDD structure, much in the same way that eta defined the ODD structure we had before. So, e.g., for D equals 6, there is a cubic invariant that takes symmetric products of E to top forms. So it's a little bit more complicated, but they do exist. And the other remark is, again, there exists a natural action of ad f on any EDD cross R plus bundle. And again, I'm not going to write down what that action is. You can find it in any of the papers that I've written above. But roughly speaking, you'll see that 3 vectors are going to move you up, and 6 vectors will move you up twice, so on and so forth. Okay, how does gdiff act on these bundles? Well, again, we can write any generalized diffeomorphism action on any of these tensor bundles as the combination of a diffeomorphism, the usual diffeomorphism, a closed 3 form, and a closed 6 form. And looking back at the adjoint bundle, let's find the form of it here, we'll notice we have a sort of GLD piece here, and we have 3 forms and 6 forms here. And so this naturally acts as an EDD cross R plus factor on fibers. So it plays well with the group structure. Everything works nicely. And again, infinitesimally, a gdiff looks something like a transport term plus an EDD piece. So let's make this more rigorous with the Dorfman derivative. So sections of E, much like they did for ODD, much like they did in conventional geometry, parameterize our infinitesimal diffeomorphisms, i.e. there exists a map, which again we'll write with the calligraphic L, that take vector fields and give you something in the Lie algebra of the generalized diffeomorphism group. And if I take a general vector field, which is a vector plus a 2 form plus a 5 form plus that weird bit, this gets mapped to the following. So you get a diffeomorphism piece, closed 2 forms and closed 3 forms and closed 6 forms. And this tangent, this tau piece, this weird piece drops out entirely.
David, you have 10 minutes left.
Perfect, thank you. So this guy looks like a diffeomorphism. This guy looks like closed forms. So again, we can write LV in a sort of EDD covariant way. We can write this. Again, this satisfies the exact same conditions that we had before. So I'm not going to write them down again. It has the exact same properties. It sort of defines a Lie algebroid up to homotopy, all this kind of stuff. Now, you should be thinking that this is quite remarkable that somehow generalized diffeomorphisms exactly play with the group structure. And it is really rather remarkable that the groups that appear in string theory precisely match the gauge structure that come from string theory as well. And if people are interested, I can talk a little bit more about how these all fit together. But I don't think I have time for that now. So in the last 8 minutes or so, I'll just quickly go through some G structures. And again, let's look at what they are in conventional geometry, just to recap this idea. Basically, most geometries that you're aware of are G structures in some sense. So let's do a definition. For G, a subgroup of GLD, a G structure is a set of tensors. For some amount, they don't have to be in the same tensor bundle or anything, that are globally non-vanishing and preserved by G. And we say, definition, they are integrable if there exists a torsion-free compatible connection. So i.e., these conditions hold. So let's go through some examples that you've probably already seen. So a Calabi-Yau structure, and let's just restrict to D equals 6 just for convenience. A Calabi-Yau structure is an SU3 structure. And it's defined by a real 2 form and a complex 3 form, sorry about the clash of notation, that satisfy these compatibility conditions. And it's integrable if and only if these are both closed. The other one you might have seen is a metric or a Riemannian structure, which is an O6 structure, and it's defined by a metric, and it's always integrable. This is the fundamental theorem of Riemannian geometry. And note that this is the maximally compact subgroup of GL6. So, okay, we've seen some examples, and normally integrability can just be translated into some differential conditions on these tensors. So when we want to talk about generalized G structures, you do exactly this, except you just translate the GL subgroups to O66 subgroups or EDD subgroups. So generalized G structures. Definition for G, now a subgroup of ODD or EDD, depending on which situation you're in. It's defined by a set of tensors, XA, 1 to n, ... brackets, same as above. And we can define integrability Again, there's a notion of a generalized connection and generalized torsion, which I don't have time to go into, but it's integrable if and only if there exists a torsion-free generalized connection compatible with the XA. So let's go through some examples that you will probably see. A generalized metric structure. Now I'm just going to restrict to 066 geometry here. I'm not going to do EDD, but they do exist. A generalized metric. This is an 06 cross 06 structure. And again, this is the maximally compact, max compact of 066. And it's defined precisely by a metric and a two-form B. So it's defined by G and B, which can combine into an object which, you know, takes two copies of E to R. It defines a genuine metric on this bundle. So all supergravity backgrounds define generalized metrics. And this is, again, always integrable. We also have generalized Calabi-Yau structures, which are SU3 structures. And these are defined by a generalized spinor. So remember, our spinor bundles were either even or odd polyforms. It's just defined by a global even or odd polyform of the manifold. And it's integrable if it's closed under the exterior derivative. And finally, one that's often used, and you see a lot in ODD generalized geometry papers, is an SU3 cross SU3 structure. And these are defined by two generalized spinors of opposite chirality. So you need one even polyform and one odd polyform. And again, this is integrable if and only if both of them are closed under this exterior derivative. Now, let me just say some of the applications of these things, and then I'll finish. So these SU3 cross SU3 structures have found applications in supersymmetric backgrounds. They found applications in understanding moduli of compactifications. They found applications in topological strings. And even in mirror symmetry. So there is really a lot of literature on these SU3 cross SU3 structures. And I think I'll stop there.
Okay, thank you very much, David, for this great talk and taking time to make this pedagogical. Do we have questions?